Okay, we're going to try to derive the equations for charge on a capacitor as a function of time and current through a circuit attached to a capacitor as a function of time for a discharging capacitor. Alrighty, so what I have here is I have a capacitor that has already been charged up. Don't worry about how, it just, that capacitor right there is already charged, and it has charge Q on both plates, positive Q, negative Q. It is hooked up to a single resistor of resistance R, right there, okay? And the current through this resistor is I, and the voltage across that resistor is delta V. So, first let's think of what this looks like at time 0. That is, as soon as I hook up this resistor to this capacitor, what happens? Okay, so let me get a pen here. Okay, so let's think about at time 0. Also, a little thicker pen. Okay, so when this first starts happening, let's call the charge on the plates is Q naught. That's like the initial charge on the plates. At the very first moment, immediately after we hook up this capacitor, this resistor, we have I naught current through the resistance R, the resistor R, and also we have V naught across R. Okay. And the reason I'm doing this is actually something for later, but I just wanted to do it here next to the picture. If I take... Let's see. I'm looking for pens. I'm not doing this on my usual tablet. I'm doing it on this like old Wacom tablet that I've got at home. How about this weird? How about a blue? Okay, here we'll do blue. Okay. Anyway, so if I do that, then at this moment, at this very moment when everything starts, I know that the potential difference across the resistor is actually the same as the potential difference across the capacitor, because it would hook up on the same, it'd be the same potential difference. So that delta V should follow the equation for a capacitor, which at that moment should be the Q at that moment over capacitance, okay? And the reason I'm going to do that is so that I can put that into Ohm's law to figure out what the initial current is in terms of the capacitor and the resistor. So I'm going to do that. So use an Ohm's law. So in this case, that would be Q naught over C for the delta V, and then R. Okay. Okay, so we'll come back to that in a bit. We're going to need that later. But for now, let's scroll down. We want to derive the Q is a function of time and I is a function of time. I know that Q will start at time 0 with Q naught, and I will start at time 0 with I naught. But what does it look like after that? Like, as time goes on, what happens? Okay, now we've talked about this in the past conceptually, but we've never done the math. So conceptually, we've said that when you first start to discharge a capacitor, it's like a lot of current all at once. Okay. So I should get some sort of function where I start with a lot of current, that current being I naught, and it should drop off over time. Okay, you can see this when you use a non-smartphone camera, the kind that you have to discharge a capacitor to do. So you can hear them charging, they make that whiny noise, and then when they discharge all at once to make one big flash of light. Okay, and they drain off slowly after that. So it's some sort of function that starts off big and becomes smaller and smaller and smaller. And we're going to see what that looks like when we get there. So, okay. So I want Q of T and I of T. Turns out if I can get one of them, that is the Q of T, I can get both because I already know something kind of cool. If I can somehow express the rate of change of charge on the capacitor, well, I know that in general, I is the rate of change of, well, actually, it's the rate of flow of charge through a specific point in a circuit. And we talked about this before, that this is like, usually you think of this conceptually as, rate of flow instead of rate of change. But if you're talking about the charge on a plate, you can think of it as a rate of change. Okay. That is, as charge leaves these plates, it's going to become current that then flows around and is the rate of change on the other plate as well. It'll be the same rate of rate of change, blah, 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 blah. Okay. So if I can express that, I can integrate to get the Q1. Okay. If I can express somehow the rate of change of Q on the plates, not only will it tell me current, but I can integrate it to get Q of T. Okay. Now we do have a little bit of a problem here. In this case, I is the rate of flow of positive charge. The rate of flow, because remember that thing with the mistake we made as humans way back when? If you are talking about positive current, you're talking about the rate of flow of positive charge. No, Cortana, I don't want you to show up. Sorry, I pushed a button no, stop it. That's probably not showing up because I have this set to record only the window, but Cortana wanted to be seen. Okay. But I is the rate of flow of positive charge. If you want to make this be the same, or if you want this red equation to be true, for this particular one, for the current to flow, charge must be leaving the plates. Like the plates have charge. The charge leaves the plates, flows around, and comes back on the other plate. Okay? So the dq dt of the plates, the rate of change of charge on the plates, is actually negative because they're losing charge. Yet I is positive in that it's flowing the way the charges would flow, positive charge. So I do have a little bit of a problem. No, Cortana. Sorry. I bet I have a button on. Okay. I think I fixed it. Okay. Boy, this video's gone downhill really fast. I haven't done one of these for a long time. What was I saying? Why did I wait until Sunday night to make this? Okay. Sorry. Okay. I is the rate of flow of positive charge, and if discharging, which we're talking about, dq dt of the plates is negative. Let me scroll a little more. There we go. Okay, so if I want I to equal dq dt, I actually am going to have to put a negative in there to actually get this to be true, that the positive current equals the rate of change of charge on the plates, because positive current needs to equal the negative of a negative number. Okay, so I do have to stick a negative in there. Okay, but to make I and dq dt actually equal, really equal. Okay, but once I've done that, it's not going to be too bad. Okay, the next thing we're going to do is we're actually going to do a loop rule to try to relate current to the delta V across the capacitor and the resistor. So let's look again. Or actually, I'll just write this down. Do a loop rule. You remember loop rules? Loop rule is my favorite. Okay, so we're going to do a loop rule. Let me just sketch this really, really fast again. This is capacitance. It's got charge on it. There's R. And it's got current I flowing through it. Okay, so at any given moment, there is charge Q, all this stuff's happening. Let's do a loop rule. So we're just going to do a loop. Here we go. Let's start the loop here and make it go around clockwise. So if I do this loop rule, I'm going to I'm going to cross the capacitor. We're just going to call that the delta V of the capacitor. That's just what we're going to call it. Minus, because I did a minus because we're about to go through a resistor. This resistor, we are going through the same direction as current, so it would be minus, and then the delta V across the resistor should be I times R. Okay, and then I'm done. Okay, equals 0. Now, for a capacitor, the delta V of a capacitor can be replaced by the charge on the capacitor divided by capacitance. So now this equation looks like this. Okay. Okay. Then, well, we just got done figuring out that current equals negative dq dt. Now, I'm going to switch to a capital Q because I've just been using a capital Q for the charge on the capacitors. So this is a rate of change of the charge on the capacitors. Oops. Yeah. Since that is true, then my little equation now becomes, well, I've still got that there, minus current becomes negative dq dt. And then I still got the R hanging out. Still an R. Okay. Okay, so now I've got that. Okay, now, what it looks like here is, well, I've got a dq in the same function as a q. What I have here is a differential equation. So we're going to have to solve it as a differential equation. You may not remember how to do this. It's okay. I'm going to walk you through it. So to solve a differential equation, first thing we have to do is separate the variables. Okay, so separate the variables. Separation of variables. You guys did this for, let me think the last time you guys did this. You definitely did it for drag forces. There was another one. I can't remember the last time you guys did this. Anyway, time to separate some variables. So, let's see. Okay, so I'm going to, what should I do? Okay, let's get everything on, well, okay, I'm just going to do this. I'm going to jump here. Separation variables means get all the Q's on one side and everything else on the other side. Okay, so all the Q's on one side, including the DQ. So this Q and this DQ need to both end up on one side together, and everything else should be on the other side. So if you do that, and I mean, that's algebra. You guys can figure that out. You end up with dq over q on one side and negative 1 RC times dt on the other side. Okay, that's what you end up with. Alrighty. Once you've done that, we're going to integrate, but we're going to integrate with different variables on each side. Okay. So on the left side, that's all about Q. Solving differential equation, remember, you do separation of variables, and then you integrate both sides with their respective variable with their respective units, respective limits. So the left-hand side, what we've got here, I want to integrate from, actually, it's easier to do the other side first. Let me talk about the other side first. We're trying to get a function of time. So what we're going to, and this side has dt in it, we're going to integrate from time 0 to time t. That's what you always do with time with these differential equations. Integrate. Is that how you spell integrate? That doesn't look right. Integrate. Ooh, I don't feel like that. Okay, tell me later that how I spell it right. Anyway, okay. Integrate from t equals 0 to t equals t. Okay, so those are going to be my limits. On the other side, we integrate from whatever q would be at time 0, okay, to whatever q would be at time t. So integrate, oh man, it's going to bug me. I don't want to stop to Google it. Integrate from, okay, so you integrate from what q would have been at time 0. So that's q naught. Remember, all the way up at the top, we made that decision. At time 0, it's q naught on the plates. Okay. To whatever q would be at q of t. So q of t. That's what we're gonna integrate to. Okay. So if you do that, here we go. Let's do that. It looks kind of funky. Okay, so we're integrating from q naught to q of t. You can also just put q with the implication that it's q at time t, but I'm just going to write out q of t. So of dq over q equals, on the other side, well, -1 over rc, those are constants, so I'm going to pull that out the front. And then I have the integration from 0 to t of dt. There we go. Okay. All right. So we integrate that and we get, well, yeah, the antiderivative of dq over q is the natural log of q. So the left-hand side ends up being natural log of q evaluated from q naught to q of t equals, here we go. Luckily, dt is just a t. Oh, shoot, I didn't mean to do that. Is a t. It's a t. So t from 0 to t. Ew, that one's going to be hard to evaluate. Okay. And then if you evaluate them, on the left here, we get the natural log of q of t minus the natural log of, come on, eraser, bottom limit. There we go. Equals, well, -t over rc. Okay. Minus 0, because evaluated at 0 is 0. Alrighty. Okay. Now, we want to solve for q of t. And that's what we want. We want to find the, we're trying to solve for q of t. So, I want to solve for q of t. It's right there. It's right there. Whenever you see a natural log, especially when it's a subtraction like this, because that's always what happens when you evaluate integrals that are natural logs, you end up with the subtraction of the limits. You always want to try to put them together, because the way you're going to solve this is by by eing it. I don't actually know what you call it. Yeah, so you need to do that trick with the natural logs, where the natural log, the difference of natural logs, or rather the difference of any log with the same base, is the same as the natural log, the log of the quotient of those two things. So like that. Like that. Okay, equals -t over rc is just hanging out over here. Okay. So we're solving for q of t is what we're doing right now. Okay. So now we're going to e it. And some kid, that's what they called it years ago when I was doing that. I don't know what you do, like if there's an actual name for it, but I mean, take everything to the e, everything is to the e power, right? Because if you do that, it gets rid of the natural log and you e it. That's all I can say. You take everything e to that power and it gets rid of the natural log, which leaves what was in the natural log behind, and you have to do it to both sides, so the other side ends up being e to the -t over rc power. Okay. And then just multiply by q naught to get q of t. And then we're done. We solved for q of t. Q of t equals q naught e to the -t over rc power. Okay. And this, in fact, is the function for the charge on the plates as a function of time. Notice that it is an e to a negative power, okay? So this is an exponential decay function where you start with Q naught amount of charge and it exponentially decays from there. Now, small note, or actually not a small note, a really important note, okay? The thing on the bottom, okay, that is RC, like the product RC, has a name, okay? It is called the time constant, okay? And we use a tau to represent it, okay? And here it is, time constant, okay? And this is a little weird. I'm not like, this is going to sound weird, like you're going to think, why do we even care about this? But it is something we like to ask you about, so you need to know about it. It is the time it takes for the charge on the plates to decrease by a factor of 1 over e. Yes, okay. So it's a time. If you work out the units, it actually is a time, weirdly, like it's in seconds. The time it takes for Q, the charge on the plates, to decrease by a factor of 1 over e. Okay. In a practical sense, I don't know if that is really necessary to know how long it takes for something to decay to it by a factor of 1 over e. But where this does become good to know is like, what time is this? Is it like 3.5 seconds or what? Is because a lot of the time you're going to be asked to graph Q as a function of time. And when you do that, knowing where this is going to help you get the curvature right. So for example, if you were making a graph of Q over T, or Q as a function of time, okay, if you were doing that, like here's Q naught. So your graph's going to start there for sure. And let's say you calculate what tau is, the time constant, and you put it on here. So it's like, okay, here's tau. It's right there. Okay. If you make a little nice dotted line that's supposed to be straight, that's supposed to be straight. Oh my goodness, I just made it worse. Okay. Supposed to be straight. I know this is an exponential decay function. It's supposed to decay, but you don't want to go under this line. Okay. So like the decay will, like, if you're sketching or whatever, ooh, that's bad. Let me try again. Okay. Ugh. All right. You can try again. It's going to asymptotically approach 0, but it's going to do it like above this line. Okay. So that's what that's good for usually, is they like to make you sketch this. Okay. I actually have a practice problem on the side that we're going to do that on. But if they tell you to make a graph and they actually care about values, they say something like, I don't know, put appropriate values on the axes or something, they're going to want to see some actual numbers. Like they actually want to know what Q naught is, and you'll write that number there. And they actually want you to mark the tau and then make sure that your line doesn't go under it. Okay. Yeah, so that's usually what that's used for. Or they'll just straight up ask you what the time constant is, frankly. Yeah. Anyway, we're almost done. Okay. Our goals were to find the equation for Q as a function of time. We did it. But we also wanted to know current as a function of time. Okay. Luckily for us, we already know that for this discharging capacitor, current is negative dq dt. So that means that current as a function of time will be the derivative of Q naught e to the negative t RC. Love taking derivatives of e's. They're so great. You just bring down, you take the derivative of the exponent, right? And you bring it down in front. So I already had a Q naught. Then the exponent was negative t over RC. So you bring down, sorry, there was already an, I'll do it this way. Okay, negative d, here we go. I should really write it out. Sorry, I got excited. Skipped ahead. Okay, so yes, we're taking the derivative of this. Okay. All right, I had that negative already. Then I got the Q naught. Okay, the exponent is negative t to the over RC. The derivative of that is negative 1 over RC. And then it keeps the old function. Love those e's. Take the derivative of it and it just comes back again. Never goes away. Okay. So, well, nice thing. Negatives cancel. Boop, boop. Okay. So what I have is Q naught over RC times e to the negative RC, which, if you look way back up here, I had that Q naught over, well, CR, same thing as RC, equals I naught. So, look at there, there it is. We had I naught equaled Q naught over CR. So we're going to, basically this is that. So I can replace all of that with just I naught. And look, another exponential decay function. Okay, so current also decays, same way, with an initial current happening. That's really big, and then it decays from there. So it's going to look basically exactly the same as this one did. It also has the same time constant. So just imagine there's an I instead of a Q, and it's the same exact graph. Okay. Which is kind of nice. Okay. I'm going to talk a little bit later on a different video about like how to find I naught and Q naught and even V naught, because you can. But I think that's it for this video because this has gotten way too long.